Hey everybody, welcome again. It's Mr. Slomka. We're going to talk about section 12.4 tonight. It is the limit at infinity and limits of sequences, which is also a limit at infinity. This is pretty cool. As of this moment, we've found limits as x approaches 0, like 100,000 times. Plus, we've found plenty of limits as x approaches 1 or -1 or 2 or 3 or 6 or pretty much any other like regular kind of nice integer number. What we're going to do today is we're going to reach past those nice numbers. We're going to reach past real numbers. We're going to reach for hyperreal numbers, which is infinity, negative infinity. This is cool. This is really, really awesome because it really gets to the definition of limit, because limit is all about approaching something and not actually what's happening at the thing itself. And infinity is a number that you can only approach. You cannot actually ever reach infinity, which is really cool. So these two things, they go hand in hand. They work out really nicely together. So let's take a look at a very nice, easy example to begin with, and we're going to do it in the oldest way that we know how to. We're going to use some tables, and we're going to use some graphing. So it says sketch the graph of f of x is equal to x plus 1 over 2x, and then it says use the graph to help you find the following limits. So we're trying to find the limit of f of x as x approaches infinity, and also the limit of f of x as x approaches negative infinity. This is not like a one-sided limit. If it was a one-sided limit, the negative sign would be over here, but it is out in front. Same thing with this one. But when I say that, I also I don't totally mean it, and I'll explain that in a little second as well. So let's talk about the graph to begin with. If you want to graph this, one of the easiest ways to do that is to do it on your graphing calculator. So I'm going to do that right here. I'm going to go to my y is equal to, and I'm going to type in my equation exactly how it looks on the page using some parentheses, and then I'm going to graph it. It's a pretty small graph, so I zoomed up a little bit so we could see it. And there you go. Perfect. Okay, cool. So you can graph this guy out on your page too, which works out pretty nicely. Take a look at how I got mine set up. I'm counting by ones on the x-axis, but I'm counting by halves on the y-axis, and that's because the y values get pretty small pretty quickly. So like my first point that I could graph, if you plotted it out, would be 1, 1, and then you'd have other points like 2 and 0.75, which would be pretty close but not quite the same, and then you could have like 3 and 0.67, which would be just a little tiny bit lower. And so what you end up having is that hyperbolic type curve that we had on our graph. Same kind of thing is going to happen over here on this other side. It's going to be a hyperbola, and it's going to follow that same kind of curve like so. If you take a look, well, we have our horizontal asymptote coming right across there. It's a little bit above the x-axis, and then we have a vertical asymptote running right there, right on top of the y-axis. So I'm just trying to do my very best to kind of create that sketch. So the graph is really, really cool, and that's awesome, but a table would be great as well. So let's see if we can get some table values. So if you start plugging these values into your calculator, into this equation right here, like the first one, that would be 9 plus 1 over 2 times 9, or that'd be 10 over 18. What that's going to give you is that's going to give you about 0.55. Now technically I should round that, but I'm not going to because it's pretty if I don't round it. So I'm going to say it's about 0.55. Then for the next one, if you use 99, that would be like a decimal that's very similar but not quite the same. It's going to be 0.505. Once again, I could round that, but I think it's pretty if I leave it how it is, so I'm going to. And then this one, 999. What we're doing right now is we are getting very close to infinity, or as close as like we can. We're working our way closer and closer and closer to infinity. So that one is going to be 0.5005. Are you starting to see that pattern that I was talking about? This is the prettiness that I like. And then for this last one, it's 0.50005. So if this table extended to one more spot out, if we went all the way out to infinity, what would belong in that box? Well, you can't type an infinity into your equation. It doesn't work that way, so you have to just kind of guess. And as I can tell, I'm pretty darn close to 0.5 every single time, and I'm a little bit higher than 0.5. I'm getting shorter, closer to 0.5, even closer to 0.5, even closer to 0.5. At infinity, it will be at 0.5, or if you wanted to write it as a fraction, 1/2. Now, some people, what they'll say is they'll go back to this graph and they'll say, oh, hey, wait, Mr. Slomka, isn't that where the asymptote is? Isn't there an asymptote right there at 0.5? And I've always been told that you can't touch the asymptote. It's you can get very close to it but not touch it. And that's true, except we haven't really spent that much time talking about infinity. So there's a little exception to the rule. You can touch the asymptote at infinity, which is kind of still following the rule because you can never really get to infinity, so you can only touch the asymptote at a place that you can never be. So it's kind of like this weird catch-22 juxtaposition kind of things, and it works out kind of nicely. So the answer is 0.5. Now, if you take a look on the opposite side of the graph, you can see that we're approaching the asymptote again. I don't think we need to make another table. I'm pretty sure that you guys know what's going to happen here. It's going to be another 0.5 or another 1/2. So it's where it's heading. You are heading towards infinity. What is the y value doing as your x value is heading towards infinity? It is getting closer to 0.5. Our answer is going to be 0.5. Cool. When we do this, this is a big number, like for a no calculator portion, and then these become very, very big numbers, and they're very big for a calculator even. In fact, if you're working on these problems for long enough, you can get like an overflow error because your calculator just can't handle the largeness of the numbers. So it says right here, it says we are dealing with some very large numbers. These numbers are getting closer and closer to infinity, or some very, very small numbers that are closer to negative infinity. So what I want to do is I want to do a little very large number practice, or very small number practice. So let's talk about some basic examples. Instead of writing the number infinity down like I would like to, what I'm going to do is I'm just going to use something that's a little bit easier for you to maybe grasp. Maybe, I don't know. VLN is going to stand for very large number. And when you see that VLN, if you want, what you can do is you can just create a very large number on your calculator like that. So what's going to happen here is what happens if you have a very large number and you add 8 to it? Well, here's my very large number. What happens if I add 8 to it? What kind of number do I get? Well, it's still a very large number. It's a little bit bigger, but it's still very much the same. It's like if you met Bill Gates and you were like, "Hey, Bill, do you want to borrow $8?" He could take the money, but he really doesn't need it. It's not gonna make that much of a difference in his bank account or his worth. Same kind of thing here. What if you have a very large number and you subtract 8 from it? So if we take our very large number and we subtract 8 from it, what kind of answer are we going to get? Well, it's still a very large number. Same kind of thing for Bill Gates. If you met Bill Gates and you saw him walking down the road and you noticed that he dropped $8 out of his pocket, that wouldn't be that big of a deal. He wouldn't need to come back and like search the streets to find the $8. He can handle it. He can make it without. All right, let's kind of continue this pattern. What if you have a very large number and you multiply it by 8? Well, it's going to be a very large number again. That's just going to make it even bigger. Some people in the past have said, "Oh man, Mr. Slomka, that's going to be a very, very large number," and I'll buy that. That's totally fine, but it's still a very large number. We're still talking about the same thing. What if you take your very large number and you raise it up to a power of 8? Well, it's still going to be a very large number. It's not going to change at all. Some people have said in the past, "Mr. Slomka, that one's a very, very, very large number," and I'll buy that. All right, now for this last one. This one's very, very interesting. Okay, so now we're not going to add or subtract or multiply, or we're not going to use powers. We are dividing. And take a look. The very large number is on bottom this time. So what's going to happen here is I'm going to start off with my 8, and then I'm going to divide by my very large number. What kind of answer do I get? See that negative sign right there? That means you need to jump your decimal point to the left 8 times. So that means there's going to be a decimal point and 7 zeros and then this 8 right here. That is a very small number. Now, when we were talking about very large numbers over here, what I was really, really trying to get to was the idea of infinity. And when I say very, very small number right here, you want to know what I'm really talking about right here? I'm actually talking about 0. Our small number is very, very close to 0. Now that's very exciting. Right here, infinity is not something you can touch. You can't grasp it, you can't really work with it, but 0. 0 I know about. 0 I can work with. I can multiply by 0, I can add to 0, I can do all kinds of things with 0, and 0's got all these cool properties that we are very, very familiar with, so we can work with them. So this is hard. This is really kind of fuzzy and difficult to work with, and you're not going to enjoy it. But this is a little bit more concrete and a little bit easier to work with, so that is something that I'm going to try and shoot for. So basically, here's my process right here. I'm going to try to make sure my very large numbers are in the denominators. I'm going to divide by them so I can create some zeros. Let's look at some limit problems. We have a limit at infinity right here, and this really just affirms what I was just showing you. If you have the limit as x approaches infinity and your x is down in the denominator, that limit is going to 0. Same thing if it is approaching negative infinity. That limit is going to 0. That's where it's headed. That's what we can work with. And that's a nice real number that you can just deal with and write down and be confident in. So let's try out some example problems now. So right here what I have is I have the limit as x approaches infinity, so we're heading towards infinity, and we have this piece right in here, 7 minus 1 over x to the 12th. Well, first things first, this looks a little scary for some people and they want to know how to deal with it, so I'll help you out with this. You could try to combine the fraction and the 7 together, but that would mean common denominators and all kinds of stuff. I don't think I want to go down that road. You could, but I don't think I want to. So here's another option. What you can do is you can actually split up the limit. So you can take the limit of 7 and then subtract from that the limit of 1 over x to the 12th. I think this is a much better choice for you to go down. It's easier to deal with the two pieces separately. So limit of 7 is really easy, and we'll get back to that in a couple minutes, but let's talk about this dude right here because this one's a little bit tougher. Your x is heading towards infinity, and that is difficult. So what's happening here is that this guy is becoming the infinity right there. It's getting very, very, very big, and it's doing it very quickly because it's got a power of 12. So this is just getting bigger, 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 very, very quickly. What happens if you take something and you divide by that very, very large number? Well, it's spelled out for you right up here. It's going to turn into a 0. So this whole thing is basically going to turn into one big fat 0. Alright, now how about that constant term? That's 7 right there. Well, the cool thing is, we've done it before, we're doing it again. Any limit of any constant term is just the constant term itself. That guy's going to be a 7 right there. Works out awesome. 7 minus 0, you get the value 7. A nice, easy first example for you. Okay, now let's up the ante a little bit. So now this one is only a single fraction, and that's kind of nicer because this one was two things, but it's also a little bit tricky because I have multiple variables. I've got x's in the top and I've got x's in the bottom, and that can be tricky. So I have a different kind of strategy that I would recommend for you to use on this guy right here. It's similar, but it's not exactly the same. So here's the thing. It's true, this is going to infinity, and it's going to do it pretty quickly, and then it's going to get multiplied by 5, so it's going to be an even bigger infinity, and then we're going to add 2, so it's going to be an even bigger number, so this denominator is getting big. And so you might say, oh, it's going to 0. That's a really good idea. But here's the other part. This guy is also going to go to infinity, or more specifically, negative infinity. So what happens when it's like infinity divided by infinity? Well, some people are going to say, well, you know, negative 5 divided by positive 5 is negative 1, and negative 18 divided by positive 18 is negative 1. So negative infinity divided by infinity is also going to be negative 1, and that is not true. It is not going to be equal to negative 1. That is a bad answer right there. So there's this crazy thing called scales of infinity, and some infinities are bigger than other infinities, which is nutty. Just so crazy. Because infinity is the largest number that never existed, and yet there are other largest numbers that never existed that are bigger than the largest number that never existed. So, oh man, that one it's hard for my brain to wrap around. But I do get that this is just, you're walking on some very thin ice trying to make the assumptions about these numbers that you would make about any kind of regular integer. So I'm not comfortable going down this road, and it's because it's a really bad idea. So let's pick a different road to go down. So here's what I'm going to suggest. Instead of dealing with this big fraction right here, what we're going to do is we're going to create small fractions. I'm going to turn every single term that I have right here into their own fraction. And the way that I'm going to do that is I'm going to follow my hint right here. Find the variable with the highest degree and divide everything by that variable. This is kind of like rationalizing. What you're doing is you find like the offensive character and you do it on top and you do it on bottom. You're multiplying by a special case of 1. It's totally legit as long as it happens to everybody. It follows all the algebra rules. So now let's see what happens to our actual problem, because some things are going to be kind of convenient. Some things cancel out. This x right here and one of those x's can cancel out, kind of like our h's were canceling out the other day. So we are going to be left with negative 1 over x. This guy right here, not a lot's going to go on with him. He's going to stay 4 over x squared. Down here in the denominator, this is the really interesting one. That's a whole x squared, and this isn't whole x squared, so they both cancel out, and the only thing you're left with is the 5. And here, this one, not a lot's going on with him. He's going to stay the exact same. So there you go. That looks a little bit better. Not a lot, but a little bit. Now let's talk about what happens when we put in some very large numbers or infinities. This guy right here, what's going to end up happening to him in this upper left-hand corner is that big number is going to go on the bottom and he's going to turn into a 0. This guy right here, he's going to turn into a 0 and he's going to do it even faster because he's got an x squared. Down here in the denominator, that's just a 5. So that 5 is going to stay 5. And then over here, that guy's going to 0 because our x is going to infinity. So what we end up with is it's kind of like direct substitution, but you're not actually going to write the infinities in because that doesn't make a whole lot of sense. So what you're going to have is you're going to have a couple zeros in the top and then a 5 and a 0 on the bottom. Now it's true, sometimes when you divide with zeros it's sticky, but this time because the zero's on top it's totally fine. 0 divided by 5 is going to just be 0. Now, a cool thing to do for this kind of problem as well is to check it. So if you wanted to check this, that would be a really, really wise choice because it's new and it's different and you might be paranoid that your answer is bad because you use this strange technique that you might not be so confident about. So if you want to check it, easiest way is with your graphing calculator. Our graph is not very exciting. It is trying to cruising along on the x-axis, then it bumps up in the middle here, and then it goes right back to cruising along on the x-axis. It is doing exactly what we thought it would do. It's just heading towards 0. There's an asymptote right at the x-axis. If you want to see that for sure, you can change your table set right here. I'm going to go start at 100 and I'm going to count by 100 so I can get to some very big numbers. And as you can tell, what we have is we've got some negative numbers that are very, very, very small and they're not going to get very much bigger. They are sticking real close to 0 and they are just going to stay close to 0 because that is the limit. Cool. There's another one on the back. Let's try a couple of these ones from the back. Okay, on the back here, what you have is you've got a couple of examples that are very similar but a little uglier. So I'm going to change my hint ever so slightly. So on the hint back here, it says find the variable with the highest degree in the denominator. So this is kind of an important thing, and I'll explain that when we get to the example that it pertains to. So once again, highest degree, we're going to hunt down that guy. First thing I notice is that we have two different pieces, so I'm going to split it into two limits like I did on the front side. This limit's no big deal, so I'll save him for later, and I'm going to work on him. What I want to do is I don't want to deal with this whole fraction as it is right now because that would be difficult. So I'm going to create small fractions for each one of these terms. The thing that I want to divide by is not just x, but I want to divide by the x with the highest power in the denominator. And that would be this guy right here, x squared. So I'm going to divide every single term by an x squared. It's okay as long as you do it to every single term. That's totally fine. So I've done it to every single one. I have not neglected a single term in the numerator or in the denominator. So now let's see what my limit is going to look like. These two x squareds are going to cancel each other out, which is going to leave you with a -1. That 4 over x squared has got to stay. It's not going to get any better. Down here in the denominator, those two guys are going to cancel out, leaving you with just a 5. And that guy's going to stay the exact same, 2 over x squared. He can't get much better. Okay, let's do some quote-unquote direct substitution. The limit of a constant term is always just the constant term, so 4/5 is going to stay. Over here, if we start plugging in infinities, -1 is going to stay -1. This thing's going to turn into a big 0 right here, so he's not going to do too much for us. 5 is going to stay 5. And that thing's going to turn into a big 0 as well, so he's not going to do too much for us. So now our problem's very easy, and it doesn't have any limits anymore. Now we're talking about 4/5 minus 1/5. 4/5 minus 1/5 means that our final answer for this one is 3/5. There is your limit at infinity. Congratulations, you've reached infinity. Let's do another one. So our next one right here has got another fraction. It's only a single one, which is nice. But take a look. You have a very big power up here in the numerator. So you might be tempted to say, okay, he's the biggest power, x cubed. I'm going to divide everything by x cubed. That's a good idea, except for when you get down into the denominator, if you divide by x cubes for both of these terms, you're going to end up with zeros. And then your whole denominator is going to be 0, and we know that that's a bad idea when you're trying to take a limit. So I don't want that. I want to avoid a denominator of 0. So I have a kind of special rules for denominators because they are kind of sensitive, especially around 0. So and I want to avoid those zeros. So in order to do that, I am going to only use the highest exponent in the denominator, which in this case is only x squared. So I'm going to divide everything by x squared. When I do that, I'm going to end up with the limit as x approaches infinity. Most of this stuff's going to cancel out, but not all of it. We'll be left with just a negative x. That guy's going to stay the exact same. Not a lot we can do with him, so we'll leave him. This one is going to cancel out and we'll be left with a 5. There you go. We won't get a 0 down there. That's good news. And 2 over x squared is just going to stay 2 over x squared. Okay, let's find out what happens when we quote-unquote direct substitute. Well, that's going to be a negative infinity. So that's a little tricky. That one's going to be a 0. That one's pretty good news. I like that. This one's going to stay a 5. He's going to be fine. And this one's going to turn into a 0. So that's okay too. Now, I like this one and this one and this one, but I really don't know what to do with that guy. It doesn't matter that it's negative. It doesn't matter that it's going to be divided by 5. It is still an infinity, and so that's a tricky thing to deal with. And we've seen limits that went towards infinity before, and we had a name for them, and the name is going to be the exact same. This is going to be a divergent limit. It diverges. So that means that your answer is no answer at all. The limit does not exist. It is not a good limit for this one right here. If you're thinking to yourself, whoa, I don't know if I trust that one, once again, if you're really kind of worried about the things that you're writing down, by all means, feel free to graph it because you will feel just a little bit more confident if you can look at that graph. So that would be my suggestion to you. So what I'm going to do is I'm going to start typing it into my graphing calculator so I can just check to see if everything is going the way that I want it to go. So there's my denominator in parentheses. I'm going to zoom and pick just a regular standard zoom. Graph looks pretty nice. Oh boy, where's it going? So now it's going kind of subtly down, and so you might think, well, maybe there's an asymptote there. Maybe, but let's zoom out a little bit. So I'm going to go back to zoom and I'm going to zoom out. You can see right there, you know, it's just cruising down. It just continues on and on and on. It's just going to be cruising even more. If we zoom out even more, it's not like flattening out at all. It's just continuing on that same kind of path. It looks really linear right now, and that makes me feel like it's going to even continue on. So here's what's going to happen. It's going to keep going down and down and down, closer and closer and closer to negative infinity. It's going to take a really long time to get there, but it will eventually get there. And because it gets to negative infinity, that means it diverges. So that's kind of the case that we have going on right down here in the box. Now here's a cool little piece of vocab for you as well. Right here, if you take a look, there's another word, and the word is converge. If you get an answer, then what happens is that your limit as x approaches infinity is set to converge at that point. So like right here, when we had the answer of 3/5, that means that your limit as x approaches infinity converges at 3/5. So it's like it's where it reaches infinity. It's where it touches its own asymptote. It's where it does all kinds of cool things, and you get a cool word to go with that as well. The word is converge. So converge and diverge are like opposites of each other. Converge is for good answers, diverge is for bad answers, or a complete lack of answers. Now the last one example that I have for you right down here, this is kind of an interesting one, and this is also one that throws people off. This one is all about sequences. We have done problems with sequences before, and they're just patterns. They're patterns of a list of numbers. And what you can do is you can plug a 1 in for n to get the first term, and then you can plug a 2 in, and a 3 in, and a 4, and a 5, and a 6, and a 7. These sequences can just keep going on, and on, and on, and on, and on. Does that sound familiar? Because it should. What we're going to try and do is we're going to try to find the last number in the sequence. The infinite number in the sequence. The very last one. The one that you would absolutely positively never be able to calculate on your own. And we're going to do it today, which is kind of cool. The way that we're going to do that is by taking the limit. We're going to take the limit as n approaches infinity. This question looks different and the directions look different, but it is the exact same thing as what was going on up here. It's just different directions. It's a way to try and kind of trip you up a little bit, and it's a way to kind of bring back some old material and attach it to the new material, which is cool. I think it's awesome. I think it's cool that we're going to find the infinite term in a pattern of numbers that we probably thought we were pretty comfortable with up until this point. So I'm excited to do it. I'm going to do it in like the exact same way. I'm not going to change too much. So our highest power in the denominator is only n. So we're going to divide everything we have by n. When I divide all those terms by n, that guy is going to lose some n's, and we're going to have just 4. 5 over n is not going to change, so he's stuck. n over n can be reduced, and that's just going to be a 1, and then our minus 1 over n is stuck as well. He's going to stay. Well, what happens when we quote-unquote direct substitute? Well, our 4 is going to stay put. That guy's going to turn into a 0. The 1's going to stay put, and that guy's going to turn into a 0 as well. Your final answer is 4 over 1, or just 4. Are you starting to pick up a pattern on how this works? I hope that you're starting to feel more confident. Here's another one. I'm going to do a redundant a bunch right here. So now our highest power down here is n squared. So we're going to divide by n squared every single time. Each term gets divided by n squared. That means that here, for our very first term, that's n over n squared, so we're going to hold on to some of our n's. We're not going to lose them all. Well, the denominator n stays. 5 over n squared is going to stay the same, nothing to cancel out there. N squared over n squared is going to be 1, and 1 over n squared is going to stay 1 over n squared. Let's talk about direct substitution. When you do your direct substitution, this one's going to go to 0, and that one's going to go to 0. The 1 stays a 1. And that thing's going to go to 0 as well. So you're going to end up with 0 over 1, or just 0. Once again, there's patterns here. See if you can kind of identify the patterns. What was the relationship between the numerator and the denominator here? What was the relationship between the numerator and the denominator here? What was the relationship between the numerator and the denominator up here? These are important things, and if you can kind of spot them, it'll help you speed this whole process up. You can kind of predict what your answer is going to be, which is something that we're going to kind of work towards. The next one right here, once again, n squared is the common thing, so we're going to be putting in n squareds. N squareds cancel out, so we'll have 4. 5 over n squared is going to stay, 5 over n squared. And right down here, you're going to end up with a 12. If we direct substitute, this is going to go to 0 and everything else stays. So it's going to be a 4 and a 0 and a 12. These guys right here can be reduced a little bit, and you end up with 1 over 3. There's your answer right there. Alright, now this last example, this one's kind of a cool one. I like this one. I like this one, and it's kind of cool because you can use your brain in a different kind of way, and you can really expedite the process, which I am excited about. So if you look here, what we have is we have another sequence, so we're going to need to take the limit, and it's split up. There's a fraction out here that's being multiplied, and there's some stuff in here. Now you might say, hey Mr. Slomka, can't we just split up and do 2 different limits? And the answer to the question is yeah you can. That is a good technique to go. And I don't really have a problem with that technique, so by all means feel free to do that. But there are some people who they just don't feel comfortable with that. And I'm actually one of them. I don't really like that technique as much. So I'm going to show you one that I like a little bit more. It's more straightforward. It follows along with the same kind of stuff that we've been working on, so I appreciate it a little bit more. Here's my technique. I actually want to FOIL everything out. I want to FOIL everything out in the numerator, and I want to FOIL everything out in the denominator, meaning I'm going to kind of multiply everything by 5, and I'm going to multiply anything by n cubed. So I'm going to, in my numerator, I'm going to have a lot of stuff. And in my denominator, I'm going to have my 6n cubed. That's actually one of the reasons why I really want to do it, because now I have this denominator. Now I know what I can divide all my terms by. Okay, now here's the part that I'm really excited about, because you're like, oh, Mr. Slomka, you're just setting us up for too much work. And it might seem like that, but I want to point out some cool things, and I think you'll like what I have to show you right here. Here's the deal. You probably identify the fact that we need to FOIL this out, and that's a good idea. But here is the other thing. Have you been watching those patterns? Something I'm noticing is that I get a lot of zeros. And I tend to get a lot of zeros at the backs of my fractions, on the top and on the bottom. That seems to happen a lot. Even down here, when we did these 3 examples, you get the zeros in the back every single time. And so what I'm thinking here is that all the terms, I'm going to end up with a whole bunch of terms, almost all of them are going to end up being zeros. And that's because they're all going to get divided by an n cubed, because of that guy right there. And so I don't really know if I need to know what they really are, because I know that they're just going to turn into a 0. So here's what I'm going to do. I'm going to kind of fake distributive property this. I know that if I take this term and I multiply it by n, that would be 5n squared. And if I multiplied it by this guy right here, that would be my biggest term. That would be 10n cubed. Now, like I said, there'll be some other terms, and they will have smaller powers of n. But I don't really think I need to know what they are. Down here in the denominator, we're going to have 6n cubed as well. Now, technically, everything is going to get divided by n cubed these two terms and everything else that we also could possibly have, that would get divided by n cubed as well. So all these ones that are going to be divided by n cubed, they won't have a high enough power to overcome this denominator. They're all going to turn into zeros. So that means that they're just useless. These guys, they both have n cubed, so those n cubes are going to cancel out, and you're going to be left with a 10 and a 6 and a whole bunch of zeros. Just a ton of them. And those zeros, they really don't matter that much because they're just zeros. So the only part that is really kind of important is your two first terms, your leading coefficients, and that's going to give you your fraction 10 over 6, which can be reduced down to 5 over 3. If you're thinking to yourself, whoa, that was too crazy and I don't like that, I need some more like rock solid mathematics, then here is a little bit more of a clear thing. If you actually do distributive property out everything, you will end up with this numerator right here. And then when you end up with that numerator right there, then you can divide everything by n cubed and you will get the zeros that we were talking about, and it'll work out just the same. There you go. There's some ideas. If you have any questions, and I wouldn't be shocked if you did, come talk to me about them. Usually this lesson is pretty light, and there's the reason for that is because there's a lot of people who want to talk to me. They have their own ideas. They want to know about infinity and their kind of concepts that they have about infinity. So if you have any questions, feel free to ask, and I would love to talk to you. See ya next video.